Now, we were talking about the law of sines before. I want to do one more example of that at least, because it's about the hardest material we have left in the course, is that ambiguous case. And then we'll complete our study of oblique triangles, that is non-right triangles, by talking about the law of cosines. And between the law of sines and the law of cosines, we said we'll be able to solve every oblique triangle quickly. Before we could still do it by dropping a perpendicular through the middle and doing a lot of algebra with two triangles. But who wants to do that when you have this nice way of solving it with one? Plus, you'll see in the textbooks using the law of sines and cosines, and you don't want to be clueless what they're doing. So you can get by without these if you're just an engineer solving your own problem, but these make life so much better. And we said, just to recall, right, it's been a while since we discussed this, that oblique triangles can be rapidly solved. Both these laws apply to every triangle. The theorem says, in any triangle, blah, right? In any triangle, that. But not everything that's true is helpful, right? And that's what's the case here. Oblique triangles can be solved quickly using either one of these laws. One, by the law of sines, by up here, I guess. Which says this: sine alpha is to A, the opposite side of alpha, as sine beta is to B, the side opposite to angle beta, as sine gamma is to C, the side opposite angle gamma. In other words, in any triangle like this, alpha, beta, gamma, it doesn't matter in an oblique triangle which angle is labeled which, as long as you put C opposite gamma, that almost looks like an alpha, doesn't it? And B opposite beta and A opposite alpha, right? Any questions on that one? Does that look familiar, hopefully? This is in the angle side, rotating around the triangle either direction. Angle side angle and side angle cases. All right. What about the other cases? Two, it can be solved quickly by the law of cosines, to be discussed today. So I'll put TBD. One great thing about TBD, it can mean a lot of different things. It could be to be decided or to be discussed or something. I will say to be decided, to be discussed. In the side angle side or side if you're going three sides of a triangle cases. And then three, not at all in the case angle, because really there you only know two pieces of information. The third angle is automatically determined once you know two, because they sum to 180. That's all the cases. So angle, there is you just have similar triangles, there's an infinite number of solutions. But in all these cases, you can completely solve them with one disclaimer in the side angle case. I'll put an asterisk here. In the side angle case, there can be no solution, one solution, or two solutions. And actually, some of these other triangles, you can get no solution also. The rules say in any triangle, these rules hold. But sometimes you can give side, side, side that's not a triangle, for instance. So I'll mention one of those. Some of these every information you give works. Like angle, side, angle always works. All right. As long as you don't put two angles that add up to more than 180 or so. All right. So we'll finish the oblique triangles today, and then we'll move on maybe to polar coordinates, the first application. As I said before, this is the last of what I consider trigonometry. The rest of the semester we'll be doing applications of it, some of which are very important, and they sometimes expect you to know in your classes that come up. But you can get by with this because you can pick up the other material. There is more to be said about trigonometry. Like in some of these problems, you'll see things like this. I want to point out how useful this is, what we're doing. This is what people use a lot in practice. Suppose there's somebody on the earth over here who's lost on Gilligan's Island or something. They're lost someplace, you don't know where they are. But you have a station here. They've got a broadcaster, and you can measure the angle of their station from this place and their angle of the station from this place. And you have measured before how far apart these are. So there's a distance here, let's call it A, and an angle here, beta, and an angle here, gamma. Can you find that missing person? Of course you can, right? Three pieces of information other than angle, angle, angle. Here you have angle followed by side, followed by angle rotating this way, or angle, side, angle rotating this way, doesn't matter. That means from geometry, that's a congruous term. There's only one triangle shape that fits that. Every triangle that has that, those three measurements has all measurements the same. You can take the other one and put it right on top of that one. So you can find who's ever lost there. And I want to make this disclaimer though. What we haven't studied is that in reality, if these positions are very far apart, so that this is actually the Earth like this, your calculation won't be accurate enough to find this person. Why not? Because we're doing plane geometry. We assume a flat Earth essentially when we make those calculations. One thing we won't do in this course is called spherical geometry. What you can do is create great arcs around the Earth, and strange things occur. Like if you take this as a line of longitude, here this is a line of latitude. Here's another line of longitude here. What do you know about these angles here and here? Well, let's say we put this at 90 degrees around here. What can you do? You can make a triangle if you took this far enough apart, whose angles are 90, 90, and 90. They add up to 270. How can that be? It's because your edges, your sides are arcs of circles in spherical trigonometry. So you lose that sum of angles equals 180 degrees. Your trigonometry is all messed up too. So when these people are far enough apart, these calculations we do here don't work because it's spherical trigonometry. We have to assume that they're close enough together that a flat Earth is a good approximation. Good enough to find the soul of the island there. So we'll make that disclaimer that this is only plane trigonometry that we do here. But once you understand this, you can look online, say on Wikipedia, Google spherical trigonometry, and you can figure it out yourself with this course. You know, it'll take you a little work, it's not trivial, but you can understand it all, having done what we do here. There's nice laws for dealing with what we call triangles on a sphere in spherical trigonometry. They're not really triangles with straight edges, they have arcs of circles as straight as their sides. All right. So that's the disclaimer on this, is this only applies to plane trigonometry. Now, let's do another example of a hard case. I want to make sure you can do this on the test in case I ask this one, right? What is the hard case in side angle side? Well, it could be a case like this where I have 10, 7 for two sides, followed by an angle. All right? And so I don't know how long this side is. I'll just draw a ray. I know it has to come over here and intersect somewhere. And maybe this angle is 40 degrees. Can I solve that triangle? We said inside, if you look at it, the first thing to do is say it's side followed by angle. This is side, side, angle. I go to the law of sines rather than the law of cosines. Law of cosines applies, but I don't use it because it's not fast. what happens is if you put side-side angle into the law of cosines, which we haven't written yet, you'll get an equation with more than one unknown. You won't be able to immediately solve it. You'll have to wind up breaking it up into two different algebraic equations and solve them simultaneously. It's a mess. Might as well drop a perpendicular, right? So it doesn't help you, even though it is true in the side-side angle case. Similarly, if you get side-side-side, the law of sines won't give you an equation that has three numbers known and one unknown. You won't be able to solve the equation there. You'll wind up writing down two equations and trying to solve algebra, and it's a mess. You might as well drop a perpendicular, right? So side-side angle says that to do this quickly, I want to use the law of sines, but this is the bad case, right? The ambiguous case.
Professor?
Solutions, one solution, or two solutions. I wonder which one it is. Well,
Professor?
I'll look at it. Yeah. Am I going off?
Would you move the camera over?
Good, right?
Yeah.
I'm going to tell you guys my story of Archimedes yet. I didn't. I told that to one of my classes this semester. You'll see me go off forgetting things like that. Mathematicians do that all the time. You ever see the movie Flubber where the Robin Williams is playing a professor and he's forgetting his own wedding because he's busy in the middle of his figuring for science. There's a lot of truth in that, unfortunately. And so some remind me when I forget like that. But Archimedes was one of the three greatest mathematicians of all time in ancient Greek. And it said that he got a job by the king, that there was this crown. And he was supposed to figure out, the king thought maybe this crown was made of an inferior metal and just plated with gold. Archimedes find out, but don't cut the crown, it might be real. So how's he going to find out whether it's all real gold without damaging it? Right? So he's sitting one day in the public bath there, thinking and thinking, and all of a sudden he realizes that his body is buoyed up by the water, that if he were to put a pure gold crown underwater, weighed against the same amount of gold, they would displace the same amount of water, and they both still balance if they balance beforehand, right? Here's a scale or something, right? But if it's got mostly inferior metal, and he weighs that out against gold, and when he puts it underwater, the crown and the other inferior metal are going to displace a different amount of water. One of these is going to go up or down. And he got so excited, he ran out of a public bath down the street saying, "Eureka, I found it, forgetting he was naked." And so you'll catch me naked sometimes, forgetting to do things and move my camera and everything else. This is what you have to do to focus in mathematics. There's other famous stories about Isaac Newton, the founder of calculus, who did exactly the same thing, forgetting it, walking up the hill and not realizing his horse is bolted off on the other hill because he's thinking so hard. Kind of stuff. Anyway, so this is good that you see me do this. Maybe I'll be a better mathematician for it. Huh? I'm in good company. All right, so here's the law of sines. That's to wake you up from half asleep still. The law of sines works like this. I want to always, with the law of sines, relate an angle and an opposite side. That's how I can get one of these three equations, right? This is this equation or this equation. Maybe I hope you can see it on mine. Or anyway, there's three different equations there. And you want to get one of those equations to relate these three knowns and one unknown. And in order to do that, you need an angle on the opposite side always. So I'm going to say sine 40 degrees is to its opposite side 7, as let's call this, if this is say gamma and C, then this could be beta and B, and this would then be alpha and A. So I need to find A, beta, and alpha out of this. So let's see, the other thing I know, here's two numbers I know, 40 and 7. I need to relate 10. I can relate that with sine beta, right? So sine beta is to 10 is sine 40 degrees, is to 7, is one of the law of sines equations. And that one has three knowns and one unknown. So I can solve for beta I know, right? Equivalently by multiplying by 10. And 10 times sine 40 degrees over 7 is equal to sine of beta. And then one solution you always know to this equation, whenever the triangle is possible, that is is that beta must be the inverse sine of this. If this is any number between -1 and 1, then there is a solution, right? Now, in the case of zero triangles, you get sine beta equals a number bigger than 1 or less than 1, and then you'll say, oh, there's no solution. So the no solution case falls right out. When you go to solve this equation, sine beta equals a number, if the number is bigger than 1 or less than -1, that's impossible, right? Remember the graph of sine looks like this. Going up and down between plus and -1 is never greater than 1 or -1, so you can't make it equal something there. That's how you determine the zero solutions case, is this number comes out bigger than 1 or less than -1. But if it's equal to 1, there's exactly one solution, or equal to -1. If it's between -1 and 1, then there's two solutions you can come up with to this equation. One of them is beta equals the arc sine of this number. So there's that one. What's another solution? Let me see how this camera works here. I guess it's okay. What's another solution? What we said last time. For a number between -1 and 1 over here, there's always two solutions to this within the possibilities of a triangle. Infinite number of solutions if you add 2k5 to them, or k times 360 degrees if you're doing degrees. But there's two solutions within what triangle measures are possible. So you look at the unit circle. We can figure out what this number is in the calculator. Let's see what it is. 10 times sine 40. Close your parentheses here. Divided by 7. Remember, if you forget to close the parentheses here, it'll take sine of 47. Right? On some calculators, some will throw an error. Oops. Throw an error. There's something on there already. 10 times. That's another way to mess up. Sine 40 close divided by 7. 0.91826. Since that's not greater than 1 or less than -1, since that's between -1 and 1, I know there's exactly two solutions. Right? Not equal, but between them. So here's what I have is a line, y, this is the y coordinate, right? Equals 0.91826, and one angle right here. What angle is that? It goes to y equals 0.91826. That's the arc sine. The arc sine is the unique angle, remember, between plus and minus 90 degrees that has a given sign between -1 and 1. And so this one, since it's between plus and minus 90 degrees, has to be the arc sine of the number. Now let's see what it is. Let's try that. You can push arc sine and then push set blue ends, and it will bring back the last answer with all its decimals. They're trying to punch it in and making a mistake, right? It takes the thing automatic. And we got about 66.7 degrees to the nearest 10. I'll put squiggly equals approximately equal to that. I've rounded it. All right. What's the other angle that's possible in a triangle?
The 180 minus 180.
Yeah, this one right here. I take 180 a straight angle minus this. By symmetry, this also has to be the arc sine, measuring this way. Arc sine of 0.91826. That makes this angle here, which is the one I'm interested in, 180 degrees minus the arc sine of 0.91826. That's reaching. So there's always two angles for a sine of equals a number between plus and minus 1. One of them is the arc sine. The other one is 180 minus that. I'll write it out in all its detail here. It's 0.91826 to 5 places, but all right. So I calculate this one. And I got 66.7 degrees. You don't need to do the arc sine again. This one, you just subtract from 180. And you got 113.3 degrees. So those are the two cases, 66.7 degrees and 113.3 degrees. And now what you realize that there's actually a little bit of danger in drawing a triangle. Sometimes you draw the triangle and it looks right, and you don't realize that there's actually a second one that applies. What have I found right here by doing this? One answer is that beta equals 66.7 degrees. As I've drawn it, that would be this angle, 66.7 degrees. Here's 40 degrees. Once I have beta and gamma, whenever I have two angles, I instantly know the third one. It's easiest to just go ahead and do the subtraction. Is 180 minus the two that I know. That's this 106.7 leaves me 112. 113.3. That's 73.3. Right. So there's the last angle. And now I can finish solving this triangle. I've got the three angles, I've got two of the sides, I just need A. So now I use the law of sines again, and I say sine alpha, 73.3 degrees, is to A as, and I can use either of the other two things, sine gamma over C or sine beta over B. I'll give you full credit on the test, whichever one you use. I'm going to go back and use the original ones because they've got less rounding in them. I did one less step rounding. I'll say this is equal to sine 40 degrees over 7. But now you begin to see that if you do these things in a different order, or use a different pair, maybe use sine beta as to B here, you can get slightly different numbers when you round. So if your number is 1 off or 2 off in the last digit, then certainly you did it correctly. You just did things in a different order so that the rounding was different. All right, now I solve this one algebraically. I could take reciprocals and say A over sine 73.3 degrees equals 7 over sine 40 degrees, which reminds you that it might have been wise to, instead of writing this form of the law of sines, remember you can write it upside down like this. Just start here and you can avoid this step if you want. All right, write the law of sines upside down, it's going to work. Now you multiply by 73.3 and you've got A equals, running out of room. I keep this on this one side. Let me, if I can do a little squiggle here for a change. A equals 7 over sine 40 times sine 73.3. I won't usually do this, but I want to break this into two cases here. So let's try that. 7 divided by sine 40 closed times sine 73.3 closed. And I've got 10.4. So if I carry these all to one decimal place, there's the answer. A is 10.4. Beta is 66.7. And alpha is 73.3. I was given 3 pieces of information, and I found the other 3. So there's 3 angles and 3 sides. That's all of it. That's the one as drawn. Let's see. 10.4. Now you do the sanity check, right? Because there's so many numbers here, it's easy to make a mistake. Add the 3 things up. 73.3 and 66.7 is, let's see, 139, 140 plus 40. Sure enough, the angles add up to 180 degrees. Looking for room again. Angle sum is correct, 180 degrees. You look for the 3 bears rule, right? The shortest side 7 is opposite the smallest angle. Yeah, the next shortest side, let's see, 10 is opposite the next smallest angle, yeah? Oh, wait a minute, is that right?
Yep.
Okay. And then, yeah, and so the angle, the side angle theorem that the larger angle goes opposite the larger side, median angle opposite the median side, so forth holds. And then you check the sum of the two shorter sides, 10 plus 7, has to be greater than the longest side. 10 plus 7 is greater than 10.4. Yep. So probably I didn't make any mistakes. I'll give that just as a word of advice on this. If you don't check it and it's right, it's still right. You're not required to check it. Be good to do so. All right. Now that's one triangle. Drawing that triangle, unfortunately, maybe oblivious to the fact that there's actually a second triangle that fits that specification that was given. So it's the one case where drawing the triangle might actually be a drawback to you. Can you see the other triangle? If I have this side length and this side length and this angle, all I have to do is swing this one over here like this, and I can still have the same side length as this one, this same side length, and this same angle, and there's a triangle that looks like that. So this is triangle 2 in green, and triangle 1 in white. Let me get rid of the ray now. And there are actually two triangles in this ambiguous problem. Let's complete the other one. And what I have is the three given pieces of information, and then I find that beta in case 2, so this is case 1 over here. Beta in case 2 is 113.3 degrees. Now, in the case that there's only one triangle, sometimes this happens, that there's only one triangle. What you'll find is when you go to calculate the last angle, let's see, we've got gamma and alpha, so gamma and beta, so we need alpha is 180 less the two angles that I found, 113.3 and 40 that I was given. Well, let's see, it's 153.3, that leaves me 26.7 degrees, right? Now I've got two of the three things. I can use the law of sines one more time and get the last side. In the case that there's only one triangle, I started to say, what you'll get is a negative angle here. So that's the other hint. When there's no triangle satisfying this, we try to solve sine equals a number bigger than 1 or less than -1. When there's one triangle, one of these angles will work, but the other angle will lead to a last angle that's negative, because they'll add up to more than 180 degrees and say, oh, there's only one possibility. But when you get two cases here, both of which have positive angles, now you know there's actually two different triangles that satisfy it. You kind of see it from the picture, right? If you draw it about, this is where the picture does shine. If you draw it about right, this is about 40 degrees, almost half of a right angle, and this one about 7 to 10 ratio, then you'll see, oh, it looks like I can draw this one and this one. So it does actually help you to draw these. Now, this is two of the three things. I need the last one. I need to find A by saying sine alpha, 26.7 degrees, is to A, and let's go back to the original triangle, sine gamma, 45 degrees, is to C, which was given as 7. So I'll solve this by taking reciprocals, right, and turn it upside down. Again, it would have been wiser to start with it upside down. Fortunately, for this one, you don't have to be wise, you only have to be intelligent, right? There's a difference, right? Wisdom, you actually have to apply knowledge. A equals 7 over sine 40 degrees times sine 26.7. And if I run this out on the calculator, again, you can do the multiplication first and then the division, or you do the division and the multiplication. Comes out the same. this closure parentheses on these angles, so I'll take 7, let's say, times sine 26.7 close divided by sine 40. A lot of these calculators close 40 anymore, it doesn't matter so much. I get 4.8, 4.9 in one decimal place. So there's this triangle solved, and now I have to look at that and see if that makes sense. This one, where this is 7, 10, 4.9. This one is opposite 26.7. This one was 40 degrees. This one is 40 degrees. And this one comes out to be 113.3. And now you see that if you add these up, let's see, these two add up to 140 plus 40 is 180. Yep. Smallest side opposite smallest angle. Second smallest side opposite second smallest angle. And the sum of these two is greater than 10. Sure enough, it passes the check. And this one looks okay too. Any questions on that one? That's the hardest problem probably with it, to do a side-side angle case of the law of sines. I think there aren't some good problems left, but that's the longest I think. All right, we're going to move this over just a bit. All right. Well, if there's no questions on that one, I'm going to move on to the law of cosines. And we'll be able to solve all oblique triangles given 3 pieces of information other than angle, angle, angle. Once we complete this. Some of these things, you feel like Danny Kaye in that famous ancient movie from close to 100 years ago. Not quite, I think it's about 90 years ago, something like that, 85. Night in the King's Court, where he's trying to not drink the poison out of the cup, but he can't remember his little rhyme to figure out which one has the poison in it. That's sometimes how you feel here doing this this stuff is you can't remember, wait a minute, if it's angle, side, angle, which one is it? If it's side, 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 which one is it? Here's a way that I was able to memorize this fairly quickly. If you have side, 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 or side, angle, side, that's the law of cosines we said, right? All the other cases is the law of sines. Because angle, angle, angle isn't a congruence there. But if you get one of these two cases, you go to the law of cosines, otherwise you go to the law of sines. So that's the hint on this, and maybe that'll make it easier when you only have to look at 2. Maybe we can do 1, 2. But that's how we learn the dance and all that. So the law of cosines is a theorem. It says the following. In any triangle labeled in the canonical way, alpha opposite A, beta opposite B, gamma opposite C, it is true that C squared equals A squared plus B squared minus 2AB cosine gamma. There's the law of cosines. And I should say that since there is no relationship between the lengths of the sides or the size of the angles and the way you label them any way you want, right? I could rotate these out and put C here and A here and B here, or I could put C here and A here and B here. I can change all these labelings around. You can also relabel the law of cosine. So the law of cosine actually has 3 different equations too, but they're all just the same equation up to relabeling actually. In other words, also the law of cosines is A squared equals B squared plus C squared minus 2AC cosine alpha. I'm sorry, BC cosine alpha. Or B squared equals A squared plus C squared minus 2AC cosine theta. All three of those are the law of cosine. But it's just the same law written with sines and angles relabeled, keeping the convention that A is opposite alpha, etc. Let's call this equation star here. That'll be our star equation. When I go to use the law of cosines, I often try and label it so I use this one of the three. Why would I want to use this one of the three? You have to be very clever to figure this one out. Why is this one maybe better than these two? It's not really because it's just relabeled, but why would this be easier for me to remember, I guess?
A squared plus B squared equals C squared.
Oh, awesome, you got it. Yeah, if you cover this up, C squared equals A squared plus B squared is something you memorized before. That's the Pythagorean theorem for a right triangle, right? This proves to you that the Pythagorean theorem does not work in non-right triangles. In non-right triangles, oblique triangles, you don't get C squared equals A squared plus B squared. You get C squared equals A squared plus B squared minus 2AB cosine gamma. We said this works for any triangle. What happens in a right triangle? Right, is this all up here? I guess it is. In a right triangle, this is a 90-degree angle, and cosine of 90 is 0, and the Pythagorean theorem is a special case. So the Pythagorean theorem is just a special case of the law of cosines when the angle here in the equation is 90 degrees. This one I think is harder to remember than the law of sines. But I'm pointing this out to you because this makes it easy to remember. If you just say, oh, it's the law of, it's the Pythagorean theorem, C squared equals A squared plus B squared minus 2AB cosine gamma. I like to think of this by the other way. Sometimes instead of labeling these alpha, beta, gamma, they'll call these angles capital A, capital B, capital C, in which case this becomes C squared equals A squared plus B squared minus 2AB cosine C. So it's easy as ABCs, right? So in that sense, we'll stick with these because that's what your book does. And that's what I think most, it's more common than the other one. But this will be the law of cosines, and then just relabel them and you get these two versions. All right. I love to prove these things when it's insightful and short. This one isn't insightful and short enough that we'll do it. We'll just say we want to be able to use this. And again, this is, you can see now why you don't apply this to right triangles, right? If you apply it to a right triangle, you just use the Pythagorean theorem, which is shorter. This still works, but you have to calculate the 0 here and then take the 0 away. Why do you do the extra step, right? So this applies to right triangles also, but right triangle trigonometry is faster. Where you just take two given information in a right triangle and write the trig relations that relates them to something you don't know. Do I have enough room? I guess so. All right. All right. That's enough. Here's a fun example. You've seen a 3, 4, 5 right triangle, right? What if I gave you a 3, 4, 6 triangle? And I said, solve this. Try applying the law of sines. It doesn't work very well. Right? You get sine of alpha is to 3 as sine of beta is to 4, for instance, if you call this A and this B. And you can't solve it, right? Because you got two unknowns. So what do you have to do? I have to write, oh, sine of gamma is to 6 as sine of alpha is to 3. Now you've got these two equations, and you do a bunch of algebra, and after a long time you figure out what those are, but it's a mess, right? It's not easy. So we should be using the law of cosines on this. You look at it and say, oh, this is side, side, side data. This time I'm going to use the law of cosines. So side, 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 and side angle side of the law of cosines. Everything else is the law of sines. Cosines will make this easy. what I'll do is I'll call, I forget which one I said I was gonna do, but I'll call this alpha, call this beta, I think that's what it is, and call this one gamma. And then the law of cosines says that c squared has pi star. The first one, c squared equals a squared plus b squared minus 2ab cosine c, or cosine gamma. 6 squared equals 3 squared plus 4 squared minus 2 times 3 times 4 times cosine of gamma. And by writing the law of cosines, I have all but one number I can solve it. Right? So that's why side is good for law of cosines. You can write all but one number. Now, how do I solve this? I just subtract over. 6 squared equals 6 squared minus 2 squared minus 4 squared equals minus 2 times 3 times 4 is minus 24 cosine gamma. Well, let's see, 6 squared minus 3 squared minus 4 squared. So I just subtracted these two over and multiplied these out. That's what I did. This is 11, and what I have is 11 equals minus 24 cosine gamma. By dividing by negative 24, I get minus 11 over 24 equals cosine gamma. And maybe immediately he shudders and I made a mistake somewhere. How can it be negative? Is that possible? It actually is possible for the cosine of the angle to be negative, right? What do you know about the cosine of an angle in a triangle? If it's an acute angle, you get a positive number, right? Think of the unit circle. For an angle between 0 and 90, when I take the cosine, it's the x-coordinate, there's an angle gamma or something. So an acute angle will have a positive cosine, but an obtuse angle, if it's bigger than 90 degrees, the cosine x-coordinate will be negative. So all that means is when you get a negative number is that gamma is going to be an obtuse angle. All right? So that's fine. We'll just take this and unworried by our experience with sine where there's two answers, we'll say, well, if cosine and gamma is that number, it must be that gamma is the inverse cosine. After all, that's a solution, right? Whenever you get cosine equal a number between -1 and 1, the inverse cosine is a solution, right? But there can be more than one solution. Why don't I worry that there can be more than one solution? It works like this. The arc cosine, if you remember, the inverse cosine has this graph. If we graph it in degrees, it goes from 0 to pi in radians or 0 to 180 degrees. This is what a graph looks like. It always gives you one answer because it's a function. That answer is the unique angle between 0 and 180 degrees that has that cosine. That's what you need in a triangle. The triangle has an angle between 0 and 180 degrees. This is the only angle between 0 and 180 degrees that has that cosine. This is the only possibility. So there's no ambiguity like there was in the law of cosines, law of sines. You just take the inverse cosine and it always works. So no ambiguity in the law of cosines. But that was a nasty case for law of sines. We'll just calculate on my calculator, as long as I put it in degrees mode and don't fat finger, et cetera, et cetera. Let's see, inverse cosine minus 11 divided by 24 gives me 117, sure enough, an obtuse angle, 0.3 degrees if I round to the nearest 10. Right? So there's the only possible answer. That's one of the three angles that I'm missing. I was given three sides, there's one angle. How do I find the other two? It is true that now that you have this angle, you can use the law of cosines again. Most people don't use it at the second step. Can you imagine why? It's long, right? It's this big clunking mess here. That's the only reason. It works, and you can use the law of cosines in your test and take a little extra time to get it. Most people, since it's shorter, will use the law of sines at the next step. This requires that I have an angle on the opposite side. Well, here's an angle. It's the only angle I have, so I have to use that one. Sine of 117.3 degrees gamma is to C, 6, as, let's look for alpha, let's say. Sine alpha is to A, 3. I can solve this now by the law of sines. And I say by multiplying by 3, I get 3/6 here, or 1/2 sine 117.3 degrees equals sine alpha. If sine alpha is this number, then alpha could be the inverse sine of that. Inverse sine of 1/2 sine 117.3 degrees. Let's see what I can get out of that. Inverse sine 0.5 times sine 117.3. And I get 26.4 degrees. There's my second angle. Whenever you have two angles, immediately go to the sum of angles equals 180 degrees theorem, because it's least likely to make a mistake, right? It's easy. It's not only is it quicker, your subtraction is less mistake prone. So finally, beta must be 180 minus the 2 that I have. Let's see, 180 take away 117.3. Oops. And 26.4 gives 36.3. Given 3 sides, I found the other 3 angles. And now I realize to my horror, wait a minute, I used the law of sines. There's another triangle maybe. Is there? Actually, the answer is no, there isn't another triangle. Why is there no other triangle possible? How do I know it? Here's what we talked about, wisdom over intelligence. You can save yourself some time here by doing this in this order. When I solved this with the law of cosines, I found the angle opposite the largest side first. Why would I do that? The largest side was 6. I used the law of cosines to find the angle opposite that largest side first with the law of cosines. Because by our triangle theorem, right, that'll give me the largest angle, right? So if I start in the law of cosines with the largest side, I'll get the largest angle. I know immediately the other 2 angles are acute angles, right? No triangle has more than one obtuse angle. If you did, the angles add up to more than 180 degrees. So this may or may not be obtuse, but the largest angle, but you can never have more than one obtuse angle. So once I find the largest angle, I know immediately the other 2 angles are acute. I don't have to do the 180 minus. That gives me an obtuse angle. There's no ambiguity here now, because I can only get an acute angle. 180 minus this one isn't a possibility. It'll make the angles add up more than 180 if I try that. So don't even try it. Then you'll find the third one is negative and say, oh, why did I waste my time? So here's where intelligence combined with wisdom gives you a break, right? Is to start, use the law of cosines with the longest side first. Then you don't have to do the 2 cases over here. All right, so these are clever tricks. If you don't get all of them, you can still muddle through this, right? Maybe you find the shorter side first. You have to consider both cases here. It still works. What I want is for you to get to the answer on the test as long as it's rattled. And I know this stuff doesn't come quickly. There's a lot of little tricks to this, as you can see. Like that. Uh-oh. Lost my page. All right, so there's one example of the law of cosines. Now, one of my favorite examples in this, since I used to work for the FAA for years, we did lots and lots of trigonometry at the FAA, the Federal Aviation Administration. I worked as a contractor to them. I didn't work directly for the FAA, but there's all sorts of airplanes with angles, and there's also spherical trigonometry as well as planes fly a long ways, right? As well as plane trigonometry. So you use plane trigonometry close and spherical trigonometry when they're far away. And this law of cosines came up frequently for solving this kind of example. Suppose I have 2 aircraft leaving an airport. simultaneously at the same time. Is what that means. For foreign students, that sometimes use these words that probably they don't mean. So two aircraft leave an airport simultaneously. English is a hard language for foreign students. It's a terribly difficult language, but it's fun because it's dramatic. Romeo and Juliet is better in English. That's why part of the reason I think that Shakespeare was such a great playwright is he had a great language to work with. Two aircraft leave an aircraft simultaneously. One heads due north. At 300 miles per hour. I'm going to write MPH just to get you used to that notation. But what does MPH mean in units? I mean, it's miles per hour. You can also write this in miles divided by hours. So we're getting used to units in this class too. When you get out of here, you can be able to read literature and so forth. So one heads north at 300 miles per hour, and the other at an azimuth or a bearing of 120 degrees. This is one of the practice problems I give you, by the way, from north, studying for the next exam. Oh, by the way, the next exam was scheduled to be the day we said is, just to make sure everybody's aware, is now scheduled for a week from today. I'm sorry, not today. Okay. It was scheduled for next time. It's now scheduled a week from next time due to the delay of the last exam. So I will put in the next couple of days some practice problems for the next test, and this will be one of them on the practice test, and be able to do the law of cosines problems like this. But see how practical these things are, right? There's lots of real cases where you're making a garden and you have the three sides. I wonder what angles those are at. Or here's an aircraft problem. The other at an azimuth of 120 degrees clockwise from north. Let me spell it out. Normally we mean heading clockwise in this case. We'll say clockwise from north. At 330 miles per hour. How far apart are they after 2 hours? I should have brought my cartoon today. Very funny. I think it's Far Side cartoon. Old one. It's the math phobic's nightmare. Waiting to get up, trying to get up into heaven, and Peter or whoever asks him, now listen here, to get into heaven, answer this question. Two trains leave simultaneously. One goes up this route, right? And the one goes up this rate, this direction. And after blah, 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 that would be a test. So important. It was kind of a funny thing. Anyway, very funny cartoon. I should have brought it, but I just have to say it now. It's not as funny when I say it. But can you imagine? Okay, so here's two aircraft. The thing you do on these applied problems is draw a picture. Often a picture gives you a big hint, right? So you draw the plane going due north, and here's my not so great aircraft, looks like a fly or something. That's going due north. We'll north up just to not confuse ourselves. And then we'll say an angle of 120 degrees clockwise tells us where the other plane heads. And so the other plane is out here after 2 hours. How far is this distance on each side? You can calculate it, right? If the plane travels at 300 miles per hour for 2 hours, right? Then you have 300 miles per hour times 2 hours. The hours cancel, and you get 600 miles. That's how long this side of the triangle is, right? Now I said, draw a picture. What you should do is get all the things you know and what you don't know that you're trying to find. So here's the other one. This airplane has a 330 miles per hour for 2 hours. You take 2 hours times 300 miles each. The hours cancel. Gives you 2 times 330 or 660 miles is this leg of the triangle, side of the triangle. Now I also want to draw the thing I'm trying to find, the distance between them. Let's call that C. Why would I call that C? Don't have to, call it D. Sometimes D is more suggestive. I'm going to call it C because I recognize all of a sudden what kind of law do I use for this? I use law of sines or law of cosines. It's clearly an oblique triangle because this is not a 90-degree angle. These are both acute because this one's obtuse. So there can't be a 90-degree angle in there. I have to use a law of cosines or a law of sines. Move this over. Which one should I do? Well, let's see. I got a side followed by an angle followed by a side. That tells me I want the law of cosine. So I'll try that one. And now you see why I put over C. I'm thinking, put C for the thing I'm trying to find. I'm thinking ahead. If I want to find this distance in the law of cosines, I want to use the one I memorized best. C squared equals A squared plus B squared, Pythagorean theorem, minus 2AB cosine gamma. Right? So I'll write that down. C squared equals A squared plus B. If I use A over here, I'm going to have to write the other version of the law of cosines. I have to think about more. A squared plus B squared minus 2AB cosine gamma is the law of cosines. And A and B, you can label whichever one you want. Let's call this A. And let's call this one B. So then I have 600 squared plus 660 squared minus twice 600 times 660 times cosine of 120 degrees. Now, if you want, you don't have to do this one in the calculator, right? You can do a unit circle, since that's a special angle, and say, oh, 120 degrees, cosine is minus a half. So you can do that immediately if you want, and recognize these things. Or you can just do the whole thing on the calculator for the reason that, I usually do these just on the calculator and don't bother to put in special angles. The reason that all these things are going to round anyway, it won't help me to get this one a little more exact because I'm going to have to round at the end anyway. So let's just run this on the calculator and say 600 squared plus 660 squared. Now, that if you needed an exact answer, that would be different. This would give you an exact answer with lots of decimal places, but we're going to round anyway, is what I'm saying. Minus 2 times 600 times 660 times negative a half. And then you look at this, because it's a lot of numbers, I recommend checking your calculator display. If you have a one number display, you're just the $5 calculator, this is where it can bite you sometimes. Let's see if it looks right. Yeah, we can check on our big display, our programmable calculator here, and we find out that we get 119.1600. Apparently 1,191,600 miles squared. That's C squared. Tells us that C is the square root of this number, which comes out to be 1,091.6 miles to the nearest tenth of a mile. 1,092 if you round it to the nearest mile. Okay, now this one I didn't say solve the triangle, so you're all done. But there's the law of cosines in the side case. Any questions on that one? right, let's do a couple more applied problems here. Again, an applied problem, start with a picture and figure out which case is it by the triangle information. Is it law of cosines or law of sines? Then just go through their calisthenics. Here's an interesting one. Solve the triangle. With A equals 3, B equals 4, C equals 8. How about this one? Side, side, side. Maybe I won't even draw it. Should.
Professor,
Yeah.
can you move the camera?
I moved it the wrong way. I actually tried to move it that time. I just moved it to the wrong side. Sorry about that. Or maybe I didn't move it far enough. Okay, yeah, thank you. Let me go in a little bit. How about this one? This is the easiest one yet. You get this in your test, you write down immediately, no solution. How can that be? In the side, side, side case, always check this. Draw the picture. Here's 3. Here's 4. And here's 8. These can't ever meet, right? If these met up here, no matter how skinny the triangle, a straight line distance 8 would be longer than going 3 over here and 4 over here. This violates the idea that a straight line is the shortest distance between 2 points. That's impossible, right? So whenever you use the sanity check, third step, if these two add up to less than or equal to this one, then the triangle is impossible. It is possible that sometimes the sum of these add up to equal to this one due to rounding too short, and you just need to carry more decimal places, and then you'll see these sum bigger than this one in some cases. But carrying enough decimals, these two always have to add up to more than this one, or it's not a triangle, right? So the theorem says in a triangle, but this isn't a triangle, right? You can't apply the law of cosines to this side, side, side case here. All right. There's some good problems in our problem set here. Here's a fun one. And the object now, this is what happens in real life, is which one do I use? Is it the law of sines or the law of cosines? Let's see. This one. This is number 9 out of one of the sections here. Suppose a pole leans away from the sun. At 7 degrees from vertical. Casting a 42-foot shadow now the angle of elevation to the top of the pole from the tip of the shadow you got your handy dandy sailor's sextant here, or maybe it's a cheap protractor and measure it from the tip of from the shadow's tip to the tip top of the pole. Sorry, from the top of the pole, from the shadow's tip, is, can't stop and still remember what I was saying, apparently, 55 degrees. How long is the pole? Forgot to measure it when I put it. I wonder how tall it is. This is a really fun kind of problem. Also, you can, I was gonna bring a problem in today and I couldn't get a hold of it. This was kind of a piece of Renaissance, problem here is to calculate the lean of the Leaning Tower of Pisa, right? You know from the engineering specifications how tall it is, right? And you can walk and measure your distance from the tower, and then you can measure the angle to the top, and you can figure out what angle it's leaning at, right? Because you know this side length here and this side length here, call it A and B and alpha. You know, side angle, you can actually solve this with the law of sines. And you assume that this is an acute angle here, so you don't get the ambiguity. But you can solve interesting problems like that, like what angle is the Leaning Tower of Pisa at? This is a similar problem, right? Here's the first thing in an applied problem. You begin by drawing a picture. It's showing up on video. Make sure I'm not too far over again. Yeah, I guess it's okay. The sun is over here, and the pole leans away from the sun 7 degrees from vertical. This is going to show you why you want to make a picture. And now you measure off 42 feet and measure up to the top of the pole 55 degrees. We said in the picture you list everything you're given and what you want to find. So 50 degrees, 7 degrees, and 42. I immediately see a problem from the picture, right? What do I need to solve an oblique triangle? I need 3 pieces of information other than angle, right? But I've only got 2. I've got this side and this angle. What you do is you use what's given in here to solve something else. If this is 7 degrees, and assuming that the ground is flat, so this is a 90-degree angle, then this one plus this one have to add up to 90, so this must be 83 degrees in here. So you use the picture to deduce this sometimes and get 3 pieces of information in the triangle. So it's 55 degrees, 42 feet, 83 degrees. That's angle, side, angle. Do I use the law of cosines or cosines? Oh, we said this is angle followed by side followed by angle. Angle, side, angle says it's the law of sines, right? It's side, and side, angle, side are law of cosines. It's not one of these, right? Law of sines will give me all but one number in an equation, and I can solve it quickly. I'll do this. In the law of sines, you want an angle and an opposite side. Oh, wait a minute, I don't have an angle and opposite side. How do I do this so I have 3 other things known? I have to begin by finding the last angle. Whenever I have 2 angles, I know the last one is 180 minus 55 minus 83. Let's see, 138 leaves me 42 degrees. Is the last angle. So I put that in. So you use the information, the picture, and fill it in as far as you can with easy stuff. Now I can do it. I've got an angle on opposite side, 42 degrees and 42 feet. And I'll say sine of 42 degrees is to 42 feet as, what do I want to find? The other thing in the picture, we said put in the given information, everything you can find, and what you want to find. Let's call this one whatever your favorite letter is. I guess we could call it C or something. So this will be gamma, and then these two be alpha and beta, and they're opposite sides. We don't worry about that so much. What we're going to say is sine of 42 degrees is to 42, as sine of 55 degrees is to C. Everything in here but C is known now. I can solve for C. Again, you can take reciprocals or you can cross multiply. It doesn't matter. Suppose we cross multiply just for fun this time, just to do it differently for people who like that. C times sine 42 degrees equals 42 sine 55 degrees. We divide by sine 42 on both sides, canceling it on the left. gives us that the C is equal to 42 sine 55 degrees over sine 42 degrees, right? I can run that on the calculator. (42 times sine 55, close the parentheses, divided by sine 42, close the parentheses, gives me 51.4. If this was in feet, then all sides will be in feet by these computations. So it's 51.4 feet tall. So there's 10th. I don't remember where the problem said around it. Here's 10th. So we did it right. All right, 51.4 feet. Any questions on that one? All right. We have time for one last quick one here. Here's a fun one. I'll just do it faster here. An example. You have a satellite up in space, all right? And I'll just draw the picture rather than write out the whole problem this time since we're short on time. Suppose you measure an angle down to two different cities. Here's a building in one city, and here's a building in another city. And you're told that the angle between these is, I think, 2.1 degrees. So double check. This is problem 7. 2.1 degrees. And the satellite can measure distances it bounces off radar or something at 370 kilometers. Those are thousands of meters, right? And 350 meters. How far apart are the cities? How about that? Here you have to complete the triangle, all right? And you're asking, what is the length of this side, C? I like to label C because if it turns out to be all of cosines, and we'll say, well, let's see, it's a side followed by an angle followed by a side. So this is one is the picture, including the thing I want to find. 2, I say side, side, side is the law of cosines. I want to write the law of cosines that uses the angle I have if I have side angle side data. So I have to write C squared equals A squared is 370 squared plus B squared 350 squared minus 2A B cosine gamma, the angle opposite the side, 2.1. And it's just like that problem we did with the aircraft. You get C squared out of this. You just had a lot of computations. Let's see, 370 squared plus 350 squared minus, et cetera, et cetera. I come up with C squared is 573.946, et cetera. So C must be the square root thereof. I'll just put square root answer. And I come out with 23.957 miles, kilometers. It has to be the same units, which will round it off to the nearest 10th. We're going to round it off. Since this is 5 or greater, we have to round it up to 24.0 kilometers. You have to put the 0 on your test because that indicates it was rounded there. It's right. It's to the nearest 10th. So include the 0 when you're showing that it was rounded to that many places. All right, let's try these problems then. Out of 8.1 on the law of sines. Look at 1 to 9 and 11. Out of 8.2, let's look at 1 to 9. Next time we'll do polar coordinates, the last topic for this next test. It will not have a whole lot of sections. You guys can ace it. You're real good at doing these triangles and then the polar coordinates with you. Thank you for your attendance.